my friend and coworker, Micha. Hey, everybody. Great to be here in Portland. This is awesome.
Happy 420.
What does that mean, Micha?
Somebody's birthday.
Oh. So welcome here. We work at Azure together, and a lot of the stuff you're going to see we use for work. We're fortunate enough to also get to work, do it for free time, so it's awesome. A couple notes. First, we have boot stickers. As you can see, we have a kind of cool logo and icon. That's courtesy of our employer. It's a little cat in a boot. Makes total sense, right? And we have those stickers, so if you have questions, we may or may not have questions at the end of the talk, but feel free if you see us just to pull aside, pester us with your trickiest questions. That's the reason we're here at the conference, to hang out with people and answer questions and learn new stuff. So feel free to talk with us. And we have tons of stickers too. And there are a couple things you can do with the stickers. You can like put them on your laptop, or some people put them on their car. Actually, a new thing, I mean, it could be a thing, it's just putting them on newborn children. I mean, maybe that's a thing we want to do. I don't know. The final note is we're going to do a lot of interactive demonstration coding, which is fairly dangerous always. So as a precaution, we've done a couple things, including turning the Wi-Fi off on this machine and prepared screenshots of code. But most importantly, our friend and associate Dave Yarwood is in the audience, and after any catastrophic failure, his task will be to start the slow clap. So I just ask you to join him, and we can lighten the moment that way. Anyway, I'll let Micha actually get to the real presentation.
Yeah, a new build tool, another one.
Such excitement.
Yeah. Thank you. But I mean, anybody who makes applications nowadays is involved with complicated things. Web applications, especially, they seem so simple, but when you actually get to the bottom of it and you start deploying them, they end up being pretty complicated. And the build is surprisingly complex and difficult to do. You have like 5 JVMs running, like make files, and all kinds of things. But being Clojure people interested in Clojure anyway, we recognize the need to manage complexity. That's why we use Clojure. It provides us abstractions and all these ways that we can manage complexity. But the build tooling hasn't really kept up with that. There's no ways to make small modules that we can compose to manage complexity, encapsulate things. So the real problem, in our opinion, is that builds
Which is our right opinion.
Right. We are unanimous that builds are processes, they're not specifications. In other words, like you can't make a program, a Clojure program that's just a big map of things you want it to do in some big specification, and then it'll generate some program that will fulfill all your wildest dreams. No, you have a process that does things sequentially, basically. And most of the tools that are out there now, Maven, Ant, whatever, all of them, are oriented around trying to make a declarative specification for what you want your outcome to be.
Gradle is actually kind of an exception, if you're familiar with Gradle. It's sort of the boot of the Java world.
Sort of.
Ish.
But basically, we're programmers. We need to be able to program. We don't want something to generate a program for us. We want to be able to, Lisp gives us all the tools that we can use to generate our own programs the way we want. So boot is what we developed to solve our own problem and fulfill our wildest dreams. And the main idea of it is that you can make small parts that each do one thing. They only do one thing, and they do that one thing well. And if you look at tools like Niskin or Maven or whatever, if you have a really successful plugin, it ends up evolving into a build tool of its own, doing everything. And it's much better to have many things that each do one thing that you can compose yourself, the user can compose themselves, than have a monolithic program that now has made all these choices for you. And although like small things, it doesn't really help you if you have many small things and you can't compose them uniformly. So that's why you end up having a big monolithic composition of them, because that's the only way you can compose them such that it works. So basically our tool empowers you to take these small pieces, put them together on the fly to make a new build process. It's pretty normal in that it uses Maven for dependency resolution, so all the things for these other systems, Maven and Niskin, will work. And we use it to build Clojure and Clojure script at Adzerk. And it has a website. So you can go there. You can ignore us right now and just go to the website.
So like I said, we're going to do some sort of interactive stuff. One of the cool things about boot is that you can start building things and using it without really having any kind of descriptor file or project file or notion of a project at all. And for this example project, I know this is a Clojure project, so we chose Java. Now we all need to build and love Java software. Actually, that's probably not true. Maybe it is. But for the purposes of demonstrating the facilities of boot, we chose to make a small Java project. So there's this Java hello world file. And the process that Java converts Java source code into JVM bytecode, it's kind of representative of all the things that build tools do, even if they're not Java. In the web's domain, we're doing various transformations on CSS preprocessors and converting and optimizing JavaScript. So we just chose Java because it's kind of representative of that thing that build tools do, which is they turn one kind of thing into another kind of thing. So what Misha's showing off now is a little boot command line action. You type in the boot command and it emits a tremendous amount of things, which he's still scrolling through. But on a smaller font size, it's actually fairly readable and well organized and nicely formatted. And it shows all of the options and tasks and so on that it supports. And one of the tasks that you can run is the Java C task. And what he shows off there is that every single task also supports this -H option. So every task you can access at the command line will have some, possibly no, well, it would definitely have documentation. That documentation may be sparse in the case of Java C. It's just showing us that we have no options. There's also boot-v, which will show you the version of boot and various relevant boot pieces of information. So what we're going to do is start working on this Java project from the command line. We're going to start compiling some Java source code. So in the source directory is our Java file, and boot is going to, Misha is going to inform boot about this source file by adding the source directory to what we call boot's source or resource paths. And that's kind of like adding that directory to boot's class path. Then we're executing a task, show, and show is a task that comes in with boot, and it's sort of a diagnostic task. It's kind of like a task that you can use to see what boot is doing in the middle of a pipeline or a series of tasks. In particular, the -F option on show will print out the value of the file set, and the file set is the build context or the set of files that the build is currently operating on. Now Misha's showing us chaining together these tasks. So we start off by informing boot about our source directory. Actually, that's a typo there. Got to do source. So -S takes a source directory. Then we call the show task, which prints the file set. Pair programming, guys. So good. Then we pipe it to the Java C task, which compiles Java, and then we show the file set again. Now, the difference between the first file set and the second file set is this .class file. Clearly, a Java hasn't been compiled, and there it is, the .class file. So we have a slide to show a little bit more about what's going on. I'll let Misha take it away.
Yeah, this is pretty typical. This is how pretty much every boot invocation works. You build up a pipeline, so you can see show -f, Java C, show -f. What gets injected into the beginning of the pipeline is your source file. And that becomes a file set, which we'll talk about in a little bit. Each task takes a file set as input, does some kind of processing, either adds, removes, modifies files to create a new file set, a new immutable file set object, which it passes to the next task, and so on. This will be familiar if you're familiar with like Ring, the middleware pattern. So let's install a jar now.
So we're just going to keep rolling with adding tasks on this thing, doing more and more things. So right now we've got our Java project compiling, and maybe we want to turn it into a jar file that's executable because we need to send this important program to someone else inside our business land or whatever the case is. So what Misha's doing is he's introduced the POM task. POM is a task that takes a number of options, like -p is the name of the project, -v is the version of the project. Those are the two pieces of information a program needs to make a POM XML file. And a POM XML file is that descriptor that goes into Maven artifacts. Then he's piping that to the jar task, which takes all of the things in the file set and puts them into a jar in a Java archive file. And that takes an option -m, and that specifies what is the main class in the artifact, which in our case is this boot.demo Java class. So in one fell swoop, he has compiled the Java, created a POM file, created a jar file, specified in the jar file what the main class is, and installed it to his local Maven repository. Now at this point, we can boot-d. We can supply the -d option to boot. And what -d does is it takes a Maven artifact name. This could be something in Clojure, or it could be, in this case, something local, and then runs another task. And one of the tasks we have is repl, and that starts a boot repl. So we're in a context now where boot is informed about our boot-demo artifact, which was installed locally. And now from the repl, there's a little song and dance we need to do to call a Java static method, main method. But sure enough, that class existed on the class path, and we just compiled and installed, and we just run it from Clojure. So, yeah. Yes. So, now we have added the source path again to boot, and we went straight into boot repl. Oh.
Man, I'm on fire today. There we go, guys.
Yeah. Okay, so he's in a repl, and the -s option, I said it adds to the file set or informs boot about where source locations are. One of the principles in boot is that everything you can do at the command line should be possible at the repl, and vice versa. Well, it's not really possible with the other direction, but we tried. So the setEnd function will take various options that inform, set and alter global build context, and the source path is one of those things. So that setEnd call he just made is analogous to the -s option we passed to boot when we were showing the previous example. So now that boot knows where our Java code is, we can actually create and initialize this boot pipeline from the repl using this boot macro, which also takes a series of tasks. Of course, the calling convention of the task is different than it is on the command line, because these are clearly functions we're calling, and it's stringing together the results of those function calls somehow. But nevertheless, it works and it does the same exact thing. So if we open another repl now and did boot-d, we would find the same result. We could add this dependency, which is installed locally, to our repl. One nice thing, yeah, so if you look at so this Java C thing, we're calling a function. Well, what is that? Well, we can call it without the boot macro, and we'll see that it's a function call, and it seems to return another function. And by itself, it's also a function, so we're generating names. But these are Clojure functions.
Function.
It is a function. So what we're doing with the boot macro and what we were doing at the command line were both actually function composition. It's slightly different syntax used to perform the composition. So we actually have.
Yeah. So
yeah. Go ahead.
Yeah. So what we did just now is we built up this pipeline, and we did it in the command line at the repl. And it's important that you be able to do them both ways, because when you're building, you need to explore a bit. And so this is what the pipeline looks like. It's kind of similar to what you would do in Unix. Unix is really powerful for having, it's well known for the power of small tools and an interface between the small tools so that you can chain them together in different ways to do a large number of things. And that's what boot provides with the boot executable and the boot macro if you're in the repl. And basically what's being provided here is the process abstraction and the connective. So you need to have these little processes that all communicate, meaning that they take the same kind of connective object as input and they emit the same kind of connective object. So you can connect them all together. In Unix, the process is a program and they pass text between each other. With boot, you have the task, which is a function, a special kind of function. And the thing that they pass between themselves is this immutable file set. So here's what a task looks like, basically. A task is a function. Def task actually returns a function. It adds some metadata. So it's basically defun plus metadata. Takes an argument, which is how you configure, that's how you parameterize tasks. So the command line options went there. The yellow is where a task can actually can have accumulated state. So it's sort of like a stateful transducer, if you know about those, or if you had a middleware factory, you could have state there. And then the green and blue is the standard middleware pattern where you have a handler that passes, after processing the file set, it passes it to the next handler, which then continues. So you have layers of middleware. we have a little macro that allows you to simplify this in a lot of cases. Sometimes you can't use this, but this is essentially what a task is doing. So you have accumulated state, handler.
So now we have shown how we can compose pre-existing tasks, but Misha's had to type in that composition multiple times now, command line, repl, and he might just storm off the stage if we ask him to do it again. So we're going to introduce a new thing, this def task, which you saw on the slide. Def task is a way for you to name compositions of either existing things or new functionality. So defining a task is like creating a plugin or extending boot. Like I said, you can either use it to compose existing things, or this is the place where you might implement new functionality. Here, we're just composing the existing things like we did before, but we're just giving this whole process a name, build. Now, you'll notice the long options that the task constructor functions are taking, like colon project or colon main. Those are the same options we were passing on the command line. They're just the long options. So boot supports short and long options at the command line, and in the REPL, all of the options are keyword arguments that are match up with the long options of the command line. So, did you do doc on build? Yeah. So one of the things def task does, so tasks are regular functions, but we prefer using the def task macro to create them just because they have metadata on them that boot can use to inform itself about them. Here, Misha is showing that the build task has a documentation string and supports -h, which was functionality automatically provided by def task. And all the other tasks also can be researched at the command line, or at the REPL the same way. Oh. So we have a problem with our thing.
No worries. I have RL wrap going on here.
Oh, nice.
Yeah, we fixed it.
So the problem is that the project, or the POM task needs, in addition to the name of the project, needs a version. We only supplied the name of the project. So Misha's going to provide the version long option for 0.1. Or who knows, maybe we're ready for 1.0. We will type it in or not.
Ship it.
Yeah.
Okay, then we do jar, then we install. Could probably just type that. Okay, don't worry about that. That warning is totally cool.
Totally normal.
It's gonna work. It's gonna work. I know. Watch. Watch.
Yeah.
See? I told you it's gonna work. You got a warning. It's gonna be awesome. Warning.
So now we've created our own new name task. It doesn't actually do anything new. It just composes existing things. But for a lot of projects, that's exactly and only what you need to do. The cool thing is that this new task we've created is first class in the sense that you can call it, compose it, just like any of the built-in tasks. Here, Misha has composed it with the watch task, which is one of the built-in tasks of Boot that is composable with a name task. It's not particularly special. The watch task leverages the fact that, like any function that follows this middleware pattern we showed, inside the innermost function, which is the piece of code that actually does the logic, task has the opportunity not to call the next task, or to call it multiple times. What the watch task does is it has a handle to that next handler, and it is monitoring the source directories, and when the source directories change, it calls that function. So because tasks are functions, that's totally, it's even fun to do, honestly.
So now we've been doing a lot of typing in the REPL, on the command line, and stuff like that, but the more astute of you will say, what if you could put that in a file? Then you'd really be set. And it turns out that, yes, this occurred to us too. The first thing you might want to do...
The original idea was we could just take a screenshot of the REPL and check that into CDS.
I keep telling you, it doesn't work that way. I mean, look at this. Like, we have a screenshot here,
Yeah.
which is pretty sweet.
Beautiful.
But
Yeah.
that's not how you do it. All right. So you can. Boot does actually support just making, an ad hoc script with Clojure in it, and you have access to all of the boot library stuff. So you can actually make a build like this, a shebang at the top. Make the file executable. You have a main method down there that can take arguments, and you can build your project like this. It'll totally work. But what you give up here is that you have to process the arguments yourself. You can't be composing different tasks on the command line like this if you have just an executable where you're handling the things in the main method. So Boot will look for a file called build.boot. in the project directory. And it'll evaluate the code in there, and then it'll take your command line options and build a pipeline out of them. So in other words, it generates the main method for you at runtime when you call it. And so you can use this to define tasks and things like that in your build.boot, which you can then use from the command line. So we want to show that.
Yeah, yes.
Yeah.
So the first cool thing, now that our task is in a file and it is in a build.boot, which is this extension that boot semi-magically knows about and does it, we can do boot-h. And the task that we created will show up right alongside all the built-in tasks with a documentation string. A poor documentation string, but an existing one. And you notice there's an extra new line there between the built-on ones and the ones in your project. So typically, we'll create these build files for a project of ours, and they're self-documenting to the extent that at least the user who types boot-h is able to discover the tasks available. That's a lot like reg t or ant show or whatever. Yes. Here we go. Fantastico. So the same way we can use watch with the repl to compose with this thing, at the command line it also composes with watch. So doing all the same stuff, we've just slightly changed the format that we're storing the build program in. It's in a build.boot file. So again, we can make full pipelines that show the things, and it's pretty sweet.
Let's make a new task, guys.
So at this point, we've only composed new existing things and given a name to that composition. But one of the more exciting things about Boot to us is that it gives you the tools you need to create new kinds of tasks. So for instance, one thing you might need to do, which is extremely important in some businesses, is you need to convert Java into Fortran. This is actually little known, but check Wikipedia. Fortran is actually just an uppercase version of Java. So it's really quite trivial to do this. Unfortunately, this is kind of a controversial view, so we haven't built this task into boot yet. So we're going to have an opportunity here to write a Java to Fortran transpiler for your satisfaction. So.
Yeah, let's talk about the file set a little bit, because we're going to be dealing with it in a minute. File set can be, the main purpose of the file set is it provides an immutable abstraction that we can use to pass information between tasks. Why is immutability good? And I know there's somebody out there playing a drinking game that every time I say immutability has to drink. So I'm sorry, dude, but I'm going to say it a few more times. Immutability is great.
That would be wasted by 10 a.m.
So immutability is great because imagine you have this pipeline of tasks, right? And each task gets a file set, and it does some things, creates a new file set that it passes on to the next guys. So it can hold on to this file set, if it's immutable, and use it later, which is key. So otherwise, you have a situation where you have a build tool where they're passing, where the file system is mutable, right? So what happens when a task wants to take this .java file and make everything uppercase? So you were typing in your editor, happily, you press the build button, and now everything's Fortran and you don't understand, right?
Truly a nightmare.
Yeah, immutability is key because tasks need to have full reign to modify any file, because what we want to achieve in the long run is have our tools doing more and us doing less. So our tools need to be able to modify anything. So the solution here is look at Git. Listen to me now, believe me later, it's like Git. There's real files underneath because the Java class path is a real thing. All the JVM tools use the class path, but we provide an immutable snapshot of it. And that's the information that gets passed between. So it's immutable. It has an API for querying it, meaning you can say what's in the file set, and it'll give you these. You can either get actual file objects or just the relative path in the class path. You can add or remove things, which returns a new immutable file set object. And you can commit, which is a mutating function that mutates, it makes the underlying files, the file system, like the immutable thing. So it's like restoring from backup or checking out a commit in Git. The underlying files are like the working set, which nobody has access to but the internals of boot. And you interact with that by making commits, just like in Git, to this file set object.
Oh, this is my part. I fell asleep.
Wake up.
Yeah, so here is the There are expanded build.boot, that includes our Fortran transpiler task. So actually, I'm going to sneak in here and point something for you. So we have an upcase def task. Actually, that should be called Fortran or whatever. Next presentation will do that. So we're creating a def task upcase, and it has a documentation string, and that would be the documentation string we'd see if we did upcase-h. Next, we have an opportunity to configure the task. So maybe our Fortran files go by another name, .php or .c maybe are also Fortran if you upcase them. They actually are. So this is where you can add options that somehow configure or parameterize this task to inform it how to do its job. Now inside this Clojure, this let expression, we mentioned earlier that this is the place where a task can accumulate state. And what we're doing here is we're initializing a resource that invocations of this task will use to store intermediate state. This is kind of what your file system is between Git commits. This is the place where you're doing your working, you prepare things, and when you're ready, you commit them to the file set. But in between those two times is when you need to work with sort of a live mutable thing. And this is kind of analogous to the way one works with transients in Clojure. Nobody cares as long as it happened inside the function. Next, inside the innermost function of this task is when we're calling a function called upcase files. And if we look at upcase files up here, it takes a directory, a working directory, and a list of files. And inside there, it calls a function, upcase bang. Now, this is such a useful thing to do that actually I created and pushed to Clojures a little library. It's super sweet. It uppercases things.
He used the install task and everything.
Yes. Yeah, I was pretty proud of myself. Unfortunately, you all weren't around to clap when I did it, but it was pretty awesome. So inside this task, we're calling this function. And this is really typical of a lot of the tasks we've written so far. There are existing things that have been written to convert one kind of file to another, whether it's ClojureScript or SCSS or whatever. And we write tasks to wrap and sort of sanitize that functionality such that we can compose these things together. Finally, at the end, we have, at the end of this task, so the task has done its work. It called upcase files on its directory, and upcase files went in and mutated a bunch of files in our working directory, this dir. And now what we do is we add this directory to the file set. This is the sort of analogous to a git add followed by a git commit. We're adding things to the file set value, committing it, and preparing it to be tasked to the next task in the chain, if there is one. Which is great. Works awesome. We could actually maybe run that one with the command line.
Yeah, let's do that.
There it is. That's glory. Cool. Now by default, boot will dump the final file set value, or rather it synchronizes that final value to a directory, to target directory. And there we have it, Fortran. There's a problem. So hold the clap. Please do boot show -d. Execute. Look at these dependencies. Let's celebrate these dependencies for a minute. Can we scroll up? I like that XAmlin library.
And JBoss.
So in the course of developing the updates library, so when I was writing this function to uppercase strings, I thought, man, this surely has been done in some other library. So I went and got every library I could from Maven and Clojures. And I brought them in because, I don't know, I was feeling it. Which now
brings us to...
Yeah, a lot of people are like me.
Brings us to pods. Anyway, so we invented this thing.
Well, we didn't invent it. Where's Toby Crawley?
Oh yeah, that's right. We didn't invent that.
Yeah. Toby Crawley of Mutant fame actually sort of had the original idea.
Yes.
There it is.
Thank you.
Yes.
You saved us all from dependency hell. And so the idea here is that we have a program in Clojure, and we have other things we want to use from Clojure, but we can't use them because they have all these dependencies that interfere with the things that are in our program. And the way they interfere is basically if you have a jar file that has a class of the same name as something that's already in the JVM, already in the class path, you have a problem. So what you do is you create pods, which are isolated runtimes, which can have their own set of dependencies, and you can evaluate expressions in there, which is really useful. You can even expand a macro in there. So you have a macro that has crazy dependencies. You could, cool things. It's easy to create, run code inside of them. They're first class, so you can have a function that produces a pod. You can have a function that takes pods as arguments and returns pods. All things you can do with regular first class things in Clojure. Although, unfortunately, some things can't be passed between pods because of the dynamic nature of Clojure. Each instance of Clojure, each Clojure runtime, has dynamically created protocols and interfaces and all these things that you can mutate inside this runtime. So it's really not possible to pass things created by Clojure to each other. But on the other hand, Clojure is really well designed. I mean, you can print just about everything that's useful. All the data that you're going to need, you can read it and print it, or make a tag literal, and that's just fine. You can pass strings, no problem.
So, like anything in boot, you can experiment with pods or any of the boot API at the repl. And Micha said that pods are first class. We have constructors for them, and you create a pod value. And it's kind of like, we come to think of them as kind of like little containers, little Docker containers almost. Because they're like little VMs that you can run arbitrary Clojure inside of. And that Clojure will not affect the program as a whole. It's isolated. I think actually recently one use of pods in a work project was I was calling out to the Amazon SQS API, which required bringing in most of Amazon's APIs for all kinds of other services unrelated to SQS. And elsewhere in that project, I was using different versions of the Amazon API, and they all brought, all these things bring in multiple logging libraries and all kinds of things that can really hose your program. So instead of doing these different things in different JVMs, which is, memory consumptive and prone to error, just run all these different things in different pods. So what Micha's doing here is he defined a pod called pod, and in the boot.pod namespace there's this constructor named pod. The pod takes an environment, which is a map describing the environment that pod should start up with. It's kind of like a Docker file for pods, if you're familiar. Now what he did is, in this pod, there's Clojure 151 was brought in. Kind of, retro Clojure version. A lot of cool things in Clojure 151, but we certainly don't want to use it anymore. But maybe we're using some library that requires something in Clojure 151. Again, that probably will never happen in Clojure, but who knows. In there, he ran the expression Clojure.version, which is a function call that prints out the version. Then he, back in the parent environment, which is the repl, he ran Clojure version, and we can see that we're in Clojure 160 at the top level. Pods, they're sweet. You want to do this one?
Sure. So here we do the same thing that we did before, only we're running Alan's awesome code in a pod. So we don't have to deal with the consequences of all those dependencies. So the first thing we do is we define the environment that the pod is going to have. And so this pod is, pod/n there is the environment of the parent. So this is, our current environment. And what we want to do is we want to have the current environment, but with different dependencies. So we're setting that pod to have a dependency on Alan's library. And then down here, this is some accumulated state that our task is going to have. It's going to own its own pod, and this pod is pretty cool. We make an anonymous pod, bind it locally, lexically, which is then in the Clojure of our Clojure with an S of our task. It's pretty lispy. So here we added a parameter to the upcase files function, which uses the pod. And you're welcome. No, thank you. Sorry.
We're done quite yet.
Yeah. So at the end we commit it, and what did I miss?
I don't know. We should run it.
Fair enough.
Boot upcase.
Oh, right.
Oh, we don't run virtual pods.
I am there.
Okay.
There we go. I'm
So-
feeling good about this one.
I feel super good too. No exceptions.
Yes.
Woo, yes.
11 failures is not an option.
So did the thing, but now, did the pod help? So we can use boot show now to look at the dependencies. And, drum roll, there's no dependencies. Success. So, to be clear, it's not like our project has no dependencies. It's just that those dependencies are isolated to the places in the build process where we need them. Yeah, we've got another probably 10 minutes, so maybe we can show some hop-on stuff and get some questions.
Sure. Yeah, if you guys have questions, we'll definitely answer them. So this is something that I'm actually doing for Hop-on, which is a web framework which doesn't use React. So
I know you're loving the sound of this, like, oh, they have their own build tool.
Those people,
web framework. Oh.
Those people have been getting to drink a lot too. The React drinking game people. React. So what we have here is this is the build.boot for hoplon.io, which I'm doing some work on. And because hoplon.io, it's a website with a lot of content in it. So doing content, and with Hoplon you do everything in Lisp, in actual X expressions. It's a Lisp program. The actual markup is a Lisp program. And doing content in Lisp in S expressions is surprisingly unfun. But there's stuff like Haml, which are basically emitting S expressions, but they do it without the punctuation, so that means you don't need to escape anything. But you do have to indent things, right? And so I wanted to incorporate Haml into so I wrote a little Haml task, which takes my version of Haml and emits S expressions from it, which becomes a Hoplon source file.
You should show some of the source.
Okay.
It's sufficiently mind-blowing. I think you'll like it. I mean, not to overstate it.
Yeah, I don't really know how.
IO?
Yeah.
Hoplon?
Content?
Getting started?
Yeah, that's the one.
So this is a pretty sweet file. Let me take it away.
Yeah, so here's a Haml-esque thing where, these, the percent means make an S expression with this thing as the car, the head, the operation. And so there's a CLJ macro. This is actually a macro that's getting called, which incorporates all this stuff, which is text, to the Haml editor as it splices these expressions into the final product.
Oh, and actually we're out of time, so cut to the meeting.
Oh,
we
yeah,
can show
well,
this part. Go down to the cool part.
The point here is that we were able to take our existing workflow and shim in a thing that takes Haml and, basically we're doing a multi-pass build, where each pass is totally independent from the others. So I can use Haml, and then I can take Haml out, and the rest of my build won't change.
And actually, we're using, you can see it on line 47, it's markdown inside of Haml, inside of Clojure, that gets converted to Clojure script, which gets converted to JavaScript, which runs in your browser.
Yeah, MD is actually a macro. MD is a macro which compiles down to an AST, which is basically Clojure script S expressions, and it does syntax highlighting using pigments in JPython in a pod. JPython in a pod.